Hello everyone, and welcome back to Learning Lane, the place where learning becomes simple, interesting, and meaningful. If you're passionate about geography, earth sciences, or preparing for competitive exams like UPSC, SSC, State PSC, or university examinations, you're in the right place. In today's video, we are going to explore one of the most fascinating branches of physical geography, geomorphology. We will understand what geomorphology is, its meaning, scope, importance, the processes responsible for shaping Earth's surface, different landforms, major theories, practical applications, and much more. So, stay with me till the end, because by the end of this video, you'll have a complete understanding of geomorphology from basic to advanced level. Let us begin with the meaning of geomorphology. The word geomorphology is derived from three Greek words, geo, meaning earth, morph, meaning shape or form, and logos, meaning study or science. Therefore, geomorphology is the scientific study of the Earth's surface features, their origin, evolution, and the natural processes that continuously shape them. Geomorphologists study mountains, plateaus, plains, valleys, rivers, deserts, glaciers, coastlines, volcanoes, and many other landforms to understand how they were formed and how they continue to change over time. Geomorphology is a major branch of physical geography and earth science because Earth's surface is never static. It is constantly changing due to natural forces operating inside and outside the Earth. Some changes occur very slowly over millions of years, such as mountain building, while others happen suddenly, like earthquakes, volcanic eruptions, landslides, or floods. By studying geomorphology, scientists can reconstruct Earth's history and predict future landscape changes. The scope of geomorphology is extremely broad. It includes the study of landforms, geological structures, weathering, erosion, transportation, deposition, river systems, glaciers, deserts, coastal processes, volcanic landscapes, tectonic movements, soil development, environmental hazards, and even planetary surfaces like those on Mars and the Moon. Today, geomorphology also uses advanced technologies such as satellite imagery, geographic information systems, GIS, drones, LiDAR, GPS, remote sensing, and computer modeling to analyze landscapes with remarkable precision. To understand geomorphology, we must first learn about the forces that shape the Earth's surface. These forces are broadly divided into endogenic processes and exogenic processes. Endogenic processes originate from within the Earth and derive their energy from Earth's internal heat. They are responsible for creating major relief features like mountains, plateaus, volcanoes, and rift valleys. These processes include tectonic plate movements, folding, faulting, earthquakes, volcanic eruptions, uplift, and subsidence. For example, the Himalayan mountains were formed due to the collision of the Indian plate with the Eurasian plate, a process that continues even today. On the other hand, exogenic processes operate on the Earth's surface and are powered mainly by solar energy and gravity. These processes gradually wear down the elevated landforms created by endogenic forces. They include weathering, erosion, transportation, deposition, and mass wasting. Exogenic processes are responsible for creating valleys, floodplains, beaches, deltas, sand dunes, and numerous other landforms. Weathering is one of the most important geomorphic processes. It refers to the breakdown of rocks at or near the Earth's surface without transporting them. Weathering occurs through three major mechanisms: physical weathering, chemical weathering, and biological weathering. Physical weathering breaks rocks into smaller pieces through temperature changes, freezing and thawing, pressure release, and abrasion. Chemical weathering changes the mineral composition of rocks through reactions like oxidation, hydration, carbonation, and hydrolysis. Biological weathering occurs due to the activities of plants, animals, microorganisms, and even human activities. Once rocks are weathered, erosion begins. Erosion is the removal and transportation of weathered materials from one place to another. The major agents of erosion include rivers, glaciers, wind, ocean waves, and groundwater. Rivers carve valleys and canyons, glaciers create U-shaped valleys, wind shapes deserts through deflation and abrasion, waves continuously modify coastlines, while groundwater forms caves and sinkholes through the dissolution of limestone. Transportation follows erosion. Rivers carry sediments in solution, suspension, saltation, and traction. Wind transports sand particles across deserts, glaciers move enormous amounts of rock and soil, and ocean currents carry sediments along coastlines. Eventually, when transporting agents lose energy, they deposit the materials they carry. Deposition leads to the formation of floodplains, deltas, alluvial fans, beaches, sand dunes, moraines, and other depositional landforms. Another important process is mass wasting, also called mass movement. It refers to the downslope movement of soil and rock under the influence of gravity. Examples include landslides, rockfalls, mud flows, debris flows, soil creep, and avalanches. Heavy rainfall, earthquakes, volcanic activity, and human activities such as deforestation often trigger mass wasting events. Geomorphologists classify landforms according to the agents responsible for their formation. Fluvial landforms are created by rivers and include waterfalls, meanders, oxbow lakes, floodplains, natural levees, deltas, and river terraces. Glacial landforms include cirques, arêtes, horns, moraines, drumlins, eskers, and fjords. Aeolian landforms are formed by wind and include sand dunes, loess deposits, mushroom rocks, and yardings. Coastal landforms include sea cliffs, beaches, spits, bars, lagoons, stacks, arches, and wave-cut platforms. Karst landforms develop due to groundwater action in limestone regions and include caves, stalactites, stalagmites, sinkholes, and disappearing streams. Volcanic landforms include volcanic cones, lava plateaus, calderas, craters, and volcanic islands. One of the most famous theories in geomorphology is William Morris Davis' Cycle of Erosion, proposed in 1899. According to Davis, landscapes evolve through 3 stages: youth, maturity, and old age. During the youthful stage, rivers actively cut deep valleys and waterfalls are common. In the mature stage, valleys widen, slopes become gentler, and meanders develop. In the old stage, the landscape becomes nearly flat, forming a peneplain. Although modern geomorphologists recognize that landscape evolution is more complex than Davis suggested, his theory remains historically significant. Another influential scientist was Walter Penck, who proposed that uplift and erosion occur simultaneously rather than sequentially. Penck emphasized continuous landscape evolution instead of fixed stages. Later, Lester King introduced the theory of pediplanation, highlighting the formation of extensive pediplanes in arid and semi-arid regions. Modern geomorphology combines these classical theories with plate tectonics, climate science, quantitative analysis, and computer modeling. Plate tectonics plays a central role in modern geomorphology. Earth's lithosphere is divided into several tectonic plates that move slowly over the asthenosphere. Their interactions create mountains, earthquakes, volcanoes, ocean trenches, and rift valleys. There are 3 main types of plate boundaries: convergent, divergent, and transform boundaries. Convergent boundaries produce mountain ranges and volcanic arcs, divergent boundaries create mid-ocean ridges and rift valleys, while transform boundaries generate earthquakes due to lateral movement. Climate strongly influences geomorphological processes. In humid tropical regions, chemical weathering is dominant because of high temperatures and abundant rainfall. In cold regions, freeze-thaw weathering and glacial erosion are more common. In deserts, wind erosion and mechanical weathering dominate due to dry conditions. Thus, different climates produce distinct landscapes across the world. Human activities have become an increasingly important geomorphic force. Urbanization, mining, dam construction, road building, agriculture, deforestation, and climate change significantly modify natural landscapes. Excessive deforestation accelerates soil erosion, while mining alters hills and valleys. Large dams change river flow, sediment transport, and delta formation. Climate change is accelerating glacier melting, increasing coastal erosion, and intensifying floods and landslides. Geomorphology has numerous practical applications. It helps engineers choose safe locations for roads, bridges, tunnels, and dams. Urban planners use geomorphology to avoid flood-prone and landslide-prone areas. Environmental scientists study soil erosion and watershed management. Disaster management agencies use geomorphic knowledge to predict floods, landslides, volcanic hazards, and coastal erosion. Geomorphology also assists in groundwater exploration, mineral prospecting, agriculture, ecological conservation, archaeology, military planning, and even planetary exploration. Some of the world's most famous geomorphological features include the Himalayas, the Grand Canyon in the United States, the Sahara Desert, the Amazon River Basin, the Great Barrier Reef, the Nile Delta, the Ganges-Brahmaputra Delta, Iceland's volcanic landscapes, and the fjords of Norway. Each of these landforms tells a story of millions of years of geological evolution. To summarize today's lesson, geomorphology is the scientific study of Earth's landforms and the natural processes responsible for shaping them. Earth's landscapes are continuously modified by internal forces like tectonic activity and volcanism, as well as external forces such as weathering, erosion, transportation, deposition, glaciers, rivers, wind, waves, groundwater, and gravity. Understanding geomorphology helps us appreciate Earth's dynamic nature while enabling us to manage natural resources, reduce disaster risks, and protect the environment for future generations. Thank you so much for watching this video on Learning Lane. I hope this comprehensive explanation has helped you understand geomorphology in a simple yet detailed way. If you found this video useful, don't forget to like, share, and subscribe to Learning Lane. Turn on the notification bell so you never miss our upcoming educational videos on geography, science, history, and many more exciting topics. If you have any questions or suggestions for future videos, let us know in the comments section below. Until next time, keep learning, keep exploring, and remember, on Learning Lane, every lesson takes you one step closer to knowledge. See you in the next video.